Hello everyone and welcome to the 22nd lecture of CS2100 discrete structures. So believe it or not, this is going to be our last lecture of the semester. And in this lecture we are going to cover more different kinds of graphs, and we are also going to introduce how graphs are connected to matrices and so on. Okay, so let's get started. So here is the outline of the part 1 of this lecture. So we are going to introduce what isomorphic graphs are and then what planar graphs are. And after that, we'll talk about bipartite graphs. Finally, we'll show what Euler's formula for planar graphs is and how it looks like. So let's start with isomorphic graphs. So two simple graphs, G and H, are isomorphic if there is an invertible function f from the vertices of G to the vertices of H, such that VW is an edge in G if and only if f of V, f of W is an edge in H. So this definition nicely connects graphs and functions, which we covered maybe a month ago. And I'll give a couple of examples of what this means. So I think it'll become more clear. This function f is called an isomorphism and is a rule for associating vertices that preserve the edges joining them. So this gives us a way of comparing graphs for something we call sameness, since a graph is not defined by how it is drawn, meaning there are many ways to draw the same graph. Okay, so here are a bunch of example graphs. And now our first example question is, which, if any, of these graphs are isomorphic to the M graph? And so if you look at the M graph more carefully, you can notice that it's basically just a straight line. And so the intuition behind isomorphism is that any of the other graphs that just unfold into a straight line are isomorphic to M. So what are these graphs? It's the graph S, V, and Z, because all of these have 5 vertices that are basically in single line, meaning you can unfold them into a line. So that's an example of isomorphic graphs. Then isomorphism has a number of interesting properties. So two simple graphs that are isomorphic must have the same number of vertices. That makes sense. The same number of edges, the same number of vertices of any given degree, the same number of cycles, and the same number of cycles of any given length. So if all these properties are true, then graphs are isomorphic. Okay, coming back to our example of a number of graphs. Now we are looking for graphs that are isomorphic to the A graph. And here we can look at degrees of vertices to find which ones are isomorphic. And if we go through all these graphs, we will notice that the R graph is isomorphic to the A graph because both graphs have 2 vertices of degree 1 and 1 vertex of degree 2 and 2 vertices of degree 3. Okay. So here is a simple example problem. So the problem asks us how many simple connected graphs with exactly 3 vertices are non-isomorphic, meaning there is no isomorphism between them. And the first hint to solve this problem is that to be connected and simple, these vertices must have degree 1 or 2. And also recall that in any graph, the number of vertices with all degrees is even. And so if we try to enumerate these graphs, which is pretty easy because they only have 3 vertices, we will quickly notice that there are only 2 such graphs that are not non-isomorphic. Okay, so we have another example problem that asks us how many simple connected graphs with exactly 4 vertices are non-isomorphic. Again, we have 2 hints. First one, to be connected simple, these vertices may have degree 1, 2, or 3. And also recall that in any graph, the number of vertices with all degrees is even. And again, as before, we can simply enumerate such graphs, which is what I did here under this text on this slide. And so there's 6 such graphs. And how do we know that they are non-isomorphic? Well, we have to take a look at the degrees of their vertices. So if degrees are different, then graphs are non-isomorphic. If 2 graphs have the same degrees of all of the vertices, then they are isomorphic. So let's look at the isomorphism rule. So graphs G and H are isomorphic. Then in this example, we want to determine what is an isomorphism function that associates vertices in G to those in H while preserving the edges joining them. And so in this case, the function maps 1 into B, it maps 2 into D, three into A, 4 into E, 5 into C, and 6 into F. So as we mentioned before when we were introducing isomorphism, there are many different ways to draw a graph. And for example, these 2 graphs, G and H, despite the fact that they look really different, they are in fact isomorphic. So you have to be careful when determining isomorphism and don't be kind of tricked by the shape of the graph. Okay. Here is another simple example problem, which asks us the same question. So what is an isomorphism function f from graphs G and H? So in this case, f maps A to 3. And you can determine this by looking at the degrees of vertices. So A has degree of 3. We are looking at the vertex in graph H that has a degree of 3, and that's number 3. So we map A to 3. Then B has the degree of 2, and so it maps either to 1 or 2. And in this case, we mapped it to 1. Then C has degree of 1, so clearly it maps to vertex 4. And D has degree of 2, and it maps to vertex 2. So that's how you determine the mapping. Okay, so the degree sequence of a graph is the list of degrees of the vertices of the graph from largest degree to smallest. So what is the degree sequence of the graph below? Let's see the node that has the largest degree. So A is 3, B is 3, and just a quick reminder, so the degree of a vertex is the number of outgoing edges. So degree of D is 4, C is 3, F is 1, and E is 1, 2, 3, 4. So we would start with 4. and then we will have another 4, which will be D, and then we will have 3 for A, 3 for B, 3 for C, and F is 1. So this is the degree sequence. Okay, so let's now introduce what the planar graph is. So a simple connected graph is planar if there is a way to draw G on a plane such that no edges cross. And such a drawing is known as an embedding of the graph in the plane. And so coming back to our example graph, G is a planar graph, and we know this because we can draw it in this way on the right, where no edges are crossing. So a graph is bipartite if the set of vertices can be partitioned into two disjoint sets S1 and S2, so that every edge in the graph has one endpoint in S1 and the other endpoint in S2. And then we can ask, for example, what are the two disjoint sets of vertices for graph G? So clearly, this would be S1 and this would be S2. If you look at the edges, they are all connecting nodes from S1 with nodes from S2. And then the graph on the right is non-bipartite graph because we cannot create such two sets. Okay, yeah, here's the solution that I drawn. So the first set is 1, 2, and the second set is 3, 4, 5. So recall that a simple graph with n vertices is complete if there is an edge between every pair of distinct vertices. And we denote such a graph with Kn. Now a simple bipartite graph with n plus m vertices partitioned into the joint sets S1 of size n and S2 of size m is complete if there is an edge connecting every vertex in S1 to S2. And we denote such a graph with K, n, m. And here is an example of a complete bipartite graph K2, 3. So as you can see, all the vertices in S1 are connected to every vertex in S2. So what's an application of such graphs? Let's say we have 3 houses, and the question is there any way to connect them to their electricity cable, TV, and telephone without one services wire crossing over or under the others? So we can model this as a K33 graph that is shown here on the right. And that's a complete bipartite graph. So the 3 houses in one set of vertices on the left and the 3 services in the other set on the right. And we must have edges from every vertex in one set to every vertex in the other set, because every house wants to be connected to all 3 services. So this question is an equivalent to asking whether K33 graph is planar. And we'll get back to this example later on to see how we can determine this. Okay, so to demonstrate that graph G is a planar graph, we have to give its embedding in the plane. So here is an example of a planar graph G. From this layout, this is not clear, but we can embed it into a plane, meaning that 2 edges should not cross, and this is the graph we get. Know that it's totally fine to draw these curved edges. Edges don't have to be straight lines. And of course, it's easy to draw different embeddings in the plane, like that rotate this and so on. So it's not like there is just one embedding. Okay, here's an example problem. So we want to use each of K1, K4, K22, K23, and K4 to describe each of the graphs below. And the question now is also which of the graphs are planar. So let's first figure out the graphs. So K4 means a fully connected graph with 4 nodes. So that's the one on the left. K14 means that it's a bipartite graph where there is 1 node on the left and 4 on the right. And this is what is happening here. So if you think about how we would draw this graph in a more of a bipartite fashion, you would put this node in the middle on the left and the 4 nodes around it on the right. And now I would draw the connections. So the one on the left is connected with each one on the right. So once you draw it like this, it's clear that this is a bipartite graph. So make sure to do that. And you can draw similar things with other graphs. It's also easy to see that all these graphs are planar graphs. None of the edges are crossing, so that you can see that right away. Okay. Then one more definition. Face of the graph is a region created by the drawing when drawn on the plane with no edges crossing. So since the plane is an unbounded surface, every embedding has exactly one unbounded face. In this example, this unbounded face is face 5. So face 5 is everything outside this graph. And if we look into the graph, face 3 is, for example, this triangle here. Face 4 is this triangle here, and so on. So faces determine these regions that planar graph defines. Okay, then the famous Euler formula tells us that for any connected planar graph G embedded in the plane with V vertices, E edges, and F faces, it must be the case that V plus F is equal to E plus 2. And so for the graph below, we have 6 vertices, we have 9 edges, and we have 5 faces. And then Euler's formula correctly tells us that 6 plus 5 is equal to 9 plus 2. So that's how we could apply this formula on this graph. Okay, so we can use the Euler's formula to check whether it holds for each of these planar graphs. So let's see if it holds. And so you can do this for each of the examples. So in this graph, on the graph on the left, this one, we have 4 vertices and we have 4 faces. And that's equal to the number of edges, which is 6. 1, 2, 3, 4, 5, 6 plus 2. So it holds. Then this graph is interesting because it has only one face, one unbounded face. And again, the formula holds. This graph has 2 faces. This is one, and the other one is the unbounded one outside of the graph. It has 4 vertices and 4 edges, and the formula holds. And the last graph has 3 faces, 5 edges, 5 vertices and 6 edges, and the formula again holds. Great. So These are just a couple of examples illustrating how you would apply the Euler's formula. Okay, coming back to our application with houses and services. So this K33 graph that we have here on the right that models this problem has 6 vertices and 9 edges. So Euler's formula then tells us that we can use the Euler's formula then to compute the number of faces. So if the graph is planar, it needs to have 5 faces. Now, notice also that every edge in this graph is on a cycle, and the shortest cycle is of length 4. And now, theorem 7 from your books in chapter 7 tells us that in any planar graph G, in which every edge is on a cycle, if k is the length of the smallest cycle, then the number of edges in G is at least k over 2 times the number of faces in G. So according to theorem 7, the number of edges in K33 is at least 4 divided by 2 times 5 is equal to 10. And this cannot be since K33 has 9 edges. And because of this theorem, we know that K33 is not planar, and we cannot solve this utilities problem. Of course, in this case, that was easy to determine maybe even just by looking at the graph because it's small. But you can imagine this problem with 1,000 houses and like 10 services. And clearly, without this theorem, it will be really hard to determine this.